Welcome to this lecture of this course on computer-aided power system analysis. In the last lecture, we have looked into the example of the Gauss-Seidel load flow analysis for a small 5-bus system, in which we have seen that Gauss-Seidel load flow technique takes a reasonably large number of iterations. For example, without any generator reactive power limit, this system was taking 69 iterations, and with generator Q limit, this system was taking 66 iterations. So, then we can imagine that if the number of iteration is if the number of iteration is this much for a small 5-bus network, so then obviously for any large power system, for example say 30-bus, 100-bus or let us say 1000-bus systems, the number of iterations taken by a Gauss-Seidel load flow analysis would be quite substantial. So, as a result, usually in the industry, Gauss-Seidel load flow method is not very much preferred. Instead of that, in the industry, usually, or rather the so called de facto method of analysis of any large power grid is essentially based on the Newton-Raphson numerical method. So, from this lecture onwards, we would be now discussing this Newton-Raphson numerical method to all its detail, but then today in this lecture we will first look into the basics of the Newton-Raphson numerical technique, so that after we do understand the basic steps, or rather the basic philosophy of this Newton-Raphson numerical method, we should be able to apply this basic steps or basic philosophy for the solution of the power flow equations. So, today we start with this basics of Newton-Raphson mathematical technique, or rather Newton-Raphson Newton-Raphson numerical method. So, today we look at basic Newton-Raphson numerical we must address, we must mention here that this particular Newton-Raphson numerical method is very powerful method, and this method has got a very large applications across all branches of science and engineering. So, then therefore, we need to give a little more attention to the understanding of this very basic Newton-Raphson numerical technique, because if we do understand this very basic technique, so then we would be able to apply it without any problem, not only for the solution of the power flow equations, but for the solutions of any set of nonlinear algebraic simultaneous equations involving any number of unknowns. So, then let us assume here that we have got n unknowns, and these unknowns are x1, x2 up to xn. Now, because there are n unknowns, so we need to have n equations. So, equations are some equation f1, x1, x2, xn is equal to 0. Please note that we are not assuming any particular form of this equation. This equation can be this equation can have any form, right? This equation can have any number of terms of nonlinearity. It simply does not matter. So, we are not assuming any particular form this equation. This equations can be of any form. Only restriction is that these are nothing but the algebraic equations. That is all, nothing else. So, Fn x1, x2, to x n is equal to 0. Now, in the Newton-Raphson technique, what we do is that we again, because this is basically a kind of numerical method. So, then what we do, that we first assume some initial point. I mean, we have to solve for x 1, x 2, x n. So, we call that this is a vector x bar. So, this is an unknown vector x bar, because this is a vector, I should say capital X, this is a vector. So, this bar is not needed. So, this is my vector, unknown vector x 1, x 2, x n t. So, this is a column vector. Now, what we start? What we start is, we start with an initial guess. X naught. So, this is a vector, so let us put a bar. So, we start with x naught. Now, if x naught is sufficiently close to this actual value of x, so then therefore, we can write if x naught is close to x 1 x, if x naught is close to x true, or rather x solution denotes this actual solution, then we can write that x solution is equal to x naught plus some delta x vector. So, that means, now what exactly we are doing? I mean, what exactly we are doing? I mean, because this is an, let us say, I mean, there are n unknowns, but to understand the basic philosophy, let us take a very simple case of two unknowns. So, x 1 and x 2. So, let us say we are taking two unknowns. So, x 1, x 2, and there is a curve, some curve, and here we are interested to find out, let us say I am interested to find out this solution. So, I am interested to find out, let us say this is my solution, I am interested to find out this solution. Now, I do not know what is the solution, that is what I am trying to find out, but then I do have some idea about this particular solution, some idea, that is in which zone it will reside and etc. I have got some idea. So, then therefore, I take an initial guess which is close to that. So, for example, so I can take an initial guess, say somewhere here. So, this is my true solution, this is my x sol, and this is my x naught, right. This is my x naught, it is actually. So, now if I have to find out x solution from x naught, so then therefore, if I can find out this difference delta x, so then therefore, if I can somehow find out this difference delta x somehow, so then I can simply add this delta x to this x naught and then simply reach at this value of x solution. So, that is the basic philosophy. Now, usually what happens that, say there is, say I am just taking a curve something like this, and I am interested, say this is the solution. Now, it is not always possible for us to find out or rather to have an initial guess which is very close to this. So, it may happen that my initial guess is somewhere, somewhere distant as compared to this solution. So, this is the x solution and this is x naught. So then what we do is that we simply try to reach that point. So then therefore, so now our objective is to find out this gap, that is basically this gap, essentially this particular distance from x naught to x solution. But because they are now quite apart, so then it is not possible for me to find out this distance in one go. So then what we do is that we try to progress toward this solution in small steps. So that means I go into a very small step, I take a slope here, take a small step, and then by this slope I then reach here, then again I take a slope and again I reach here, then I take again a slope and then again I reach here. So then therefore what we do is that we take some, we simply calculate, let us say delta x1, then so this is x naught, so then this point, so this point is let us say x1. After this I calculate here, again I do this sum calculation, whatever is that calculation that we will actually we will now just now discuss. After that we calculate delta x2, some distance, then we proceed, then we reach this point is x2, and then we keep on doing this, say this is, after that I again do this delta x3, and then we reach this solution. So what we have done here, essentially we have started with an initial guess and then we have calculated small distances and tried to approach my solution. Now how have we done this some small distance? Basically what we have done is, here we have simply calculated the slope at this point, and then we have moved along this slope by a small distance and then updated my solution. Then again when I reach at this point x1, again I have calculated this slope at this point, and then again I have moved towards the solution and then again updated my solution vector, and then again I have moved along with the direction of this particular slope at this point and then again updated the solution. So if I do this process hopefully, and if I can ensure that I will be reaching at this, if I can ensure that if we are moving into the correct direction, ultimately we would be reaching at the solution. So then what we are doing, we are essentially calculating the slope at this point and then we are updating the our solution vector. Now initially when we start, so then what we are saying, that we are saying that let my initial guess is x naught, and I assume that my solution is, actual solution is x naught plus delta x. So my task is to find out this value of delta x. So then therefore if I assume that this is my solution, x solution, so then therefore f1 x solution, that is f1 x naught plus delta x be 0. Similarly f2 x naught plus delta x would be 0, and dot 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 f naught x naught plus delta x would be 0. Now my objective is to calculate this value of delta x, because we have already assumed x naught, and if I am able to find out delta x, so then I will simply add this value delta x and then find out the true solution. So now what I have is, so I have got f1, so I am now expanding it, x1 plus delta x, delta x1, then x2 plus delta x2 dot 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 xn plus delta xn is equal to 0. Now, if these values are small, delta x1, delta x2, delta xn are small, that is, if I have just travelled by a very small distance from let us say x naught with delta x. So, then therefore, for all practical purpose delta x1, delta x2, delta xn, this particular equation can be linearized at this point. So, then here what we do, we simply apply the standard Taylor series expansion. So, what is that Taylor series expansion? So, we just apply Taylor series expansion. So, in that Taylor series expansion what we have is f1. So, we would be now for the brevity x naught plus delta x is given by, this is the standard Taylor series expansion, f naught of x naught plus del f1 del x1 into delta x1 plus del f1 del x2 into delta x2 plus dot 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 del f1 into delta xn into delta xn is equal to 0. Here please note that we have simply neglected all the higher order terms, saying that these values of delta x1, delta x2 and delta xn are very small. So, then therefore, if we take these higher order terms, what I will have, we will have simply delta x1 square, delta x2 square, delta xn square. Now, because this value delta x1, delta x2 and delta xn are already small. So, if we take their square, they would be even lower. So, then for all practical purposes they will be all be neglected. So, then this is the final expression. Similarly, for f2, from this equation f2 x naught plus delta x is equal to f2, again the standard Taylor series expansion delta f2 delta x1 into delta x1 plus delta f2 delta x2 plus dot 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 dou f1 dou xn delta xn is equal to 0. Similarly, we do this operation for all this. So, fn x naught plus delta x is equal to fn of x naught plus dou fn x1 into delta x1 dou fn dou xn delta xn is equal to 0. So, then therefore, what we have, so now if we now collect all these equations together and write them in a matrix form. So, what I have is f1 x naught, f2 x naught dot 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 fn x naught is equal to plus here it would be second row would be del f2 del x1 del f2 del x2 del fn del xn dot dot dot, then del fn del x1 del fn del x2 del fn del is equal to 0. So, if we now write, so this is a matrix equation. So, now if we do write down this matrix equation in a more succinct form, what I get is I write it as f vector f x naught plus, this is called this Jacobian matrix, matrix J into vector delta x bar is equal to 0, where vector x naught is equal to f1 x naught bar, f2 x naught bar dot 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 fn x naught bar transpose. So, we are actually denoting this vector as, so this vector is vector x, which is a function of x naught. This is delta x vector and this is the Jacobian matrix. Now, what is the size? Size is n cross 1. This has also got size n cross 1. So, and this has got a size n cross n. So, this is a square matrix. Now, in this expression, what is meant by this f1, which is a function of x naught? It means, basically it means that I have a function f1 x2 x2 x is equal to 0. So, when I say, so then here I can write down, for example, here, so this equation for example can be written as f1 is a vector of x is equal to 0, where this vector x is already defined. Now, when we say that f1 x naught, it means that we evaluate the function f1 with the values of vector x naught. So, then therefore, what we do? We simply take the initial guess x naught. So, then therefore, we know all the numerical values and we substitute these numerical values in this expression, whatever is that expression. Now, because this initial guess is not the solution, because this initial guess is not the solution, so then therefore, this expression when we do evaluate f1 with this value of x naught, this expression will not be equal to 0. Similarly, when I say that f2 x naught, that only means that we are evaluating the function f2 with the values given by x naught, and again as x naught is not the solution or rather is not the true solution. So, then therefore, when we do evaluate f2 with this value x naught, this will also not be a 0 quantity. Similarly, all the other functions when they are evaluated with the values given by x naught, they would be non-zero. So, then therefore, in general, so then therefore, this particular vector would be a non-zero vector. So, it would be a non-zero vector, so it would be a non-zero vector. So, f x naught would be a non-zero vector. Now, what is about this Jacobian? Now, we want to solve this delta x 1, delta x 2, delta x n. Now, from this equation what I can write is, from this equation we can write is that j into delta x bar is equal to minus f x naught bar. So, then therefore, from this it is very easy to find out J inverse into minus now because this is a square matrix, this is a square matrix, and if this is an invertible matrix, and or rather if this is an non-singular matrix, then it will be invertible. So, this is a square matrix, and if this is an non-singular matrix, it will be invertible. Now, the point is, if we have to do this numerical analysis, now remember this is known, this vector is known, this vector is known because we have evaluated them. So, basically we have evaluated each and every function f1, f2, f10, fn with this vector x naught, and we have calculated their values. But how about this matrix J? From where we would get that numerical values of this matrix J? So, answer lies is that first we would calculate their analytical expression, and then we will substitute the values of x1 naught, x2 naught, x3 naught into each of this analytical expression and find out their numerical value. So, then therefore, what we write is that this matrix J would be evaluated at x is equal to x naught. So, then therefore, what we will do? We will first find out the analytical expression of all these partial derivatives, because f1 is a function of x1 to xn. So, then therefore, this partial derivative or rather all these partial derivatives will also be a function of x1 to xn. So, then therefore, we would be evaluating all these partial derivative functions with the values of x naught. So, then therefore, we would find out the numerical values of all these elements of this matrix J, and then therefore, we would be able to find out this numerical matrix J. Once we find out this numerical matrix J, we can simply perform this numerical calculation. So, from here we would find out delta x. Once we find out this delta x, then what we will do? We update our solution x1 as x naught plus delta x. So, this is my new solution. So, now we have to cross check whether this is my true solution or not. So, then what we will do is we will evaluate all these functions, evaluate all functions with x1. Evaluate all functions with x1, right. Now, if x1 is really the true value, true solution, that is if we have been able to find out this particular vector such that x1 is really the true solution. So, then therefore, f1 of x1, f2 of x1, fn of x1 would be identically 0, but in practice because there are numerical values, if x1 is very close to the true solution, then this value would be almost equal to 0. So, then therefore, the difference between 0 and this numerical value would be pretty small. So, then therefore, to check whether this x1 is really the true solution or not, what we do is we simply calculate the magnitude of all this quantity, magnitude, we calculate magnitude, we calculate magnitude of all this quantity, right, and we take their maximum value, calculate error E is equal to maximum of this magnitudes. So, this is also magnitude, this is also magnitude. So, we calculate all their magnitudes. Now, if x1 is the really the true solution, so then therefore, their magnitudes would be almost equal to 0, all these values, I mean all these functional values would be almost equal to 0. So, then therefore, if we take the maximum of them also, so then therefore, this maximum quantity would be also almost equal to 0. So, then therefore, if that maximum quantity is less than some convergence value or rather less than some particular threshold value, that is very small value. So, then we can say that for all practical purpose these values are almost equal to 0. So, then therefore, if we take our say our epsilon to be as we have discussed that 1.0 into e to the power minus 12, that is equal to 10 to the power into e to the power minus 12. So, then therefore, if this value of E is less than this value, so then therefore, this value of f1 evaluated at x1 is different from 0 only after 13th decimal point. Similarly, the value of f2 evaluated at x1 is different from 0 is only after 12th or 13th decimal point. So, then therefore, because their value is different from 0 only after 12th or 13th decimal point. So, then therefore, for all practical purpose as calculation we can take their values to be 0, that means we have found out the solution. If not, if these values, if this maximum value is less than this, I mean if this maximum value of E is more than this, so that means there is at least one value, there is at least one function value which is not different from 0, right, or rather which is basically different from 0 significantly. So, then therefore, we have to reiterate it. So, then what do we do? So, if this value of E is still more than E or rather still more than epsilon, so then what we say that there is at least one functional value which is still significantly more than this 0 value. So, then therefore, we have to reiterate. So, then what we do? We again assume that let my true solution is let us say x2 and I again do this delta x for the next iteration, and then we again do the same thing with this value and keep on doing the same thing till this value of delta x becomes very small. So, then what we do is after we get this, if this value of E is more than E, so then we again evaluate x2 or rather then again we do the same thing, that is we again evaluate at x1 plus delta let us say x1, f2 at again we evaluate it delta x, again we evaluate fn by doing this Taylor series expansion etc., and then again we again recalculate these values of delta x again, and then again we update x2 as x1 plus delta x, again check whether any of these functional values evaluated at x2 is significantly more than 0 or not. If it is not, then we converge. If it is, we say, if it is, then we again do this same calculation at x2 plus delta x, this is f1, f2 at delta x dot fn x2 at delta x, and we keep on doing this iteration till we reach the convergence. So, this is the basic Newton-Raphson method. So, this is the basic Newton-Raphson method, and we will apply this basic Newton-Raphson method for the solution of the power flow equations in the next lecture. Thank you.